Professor Simpson back here again as promised now with video for 12.2 entropy. As we left off, video 12.1 talked about the idea that spontaneity was going to be affected by changes in enthalpy, but there was something else that was affecting whether or not a process was spontaneous. And we left off there by saying that other thing, that other concept is entropy. So in this section, let's get into that. What exactly is entropy and how can we use or predict entropy changes for a particular system? So as always, here are our learning objectives. So please pause the video and write these in your notes. I have split 12.2 into two videos here. So in our first video, we are going to define entropy and explain the relationship between entropy and microstates. And in our second video, we will get to predicting the change in entropy. So in this first video, first let's define entropy, and we're going to define it as measure of disorder or randomness in a system. And I will say again here that spontaneity is favored by an increase in entropy. So similar to saying spontaneity was favored by an exothermic process, but not always, same thing here. It's going to be favored by an increase in entropy, but it doesn't always have to have an increase in entropy in order to be spontaneous. Now let's talk about microstates with regards to entropy. So you can see here the definition for a microstate: specific configuration and of the locations and energy of the particles in a system. So in this example, we're going to define the system here as this box with these four particles or atoms in the box, and you can see there are four different particles of different color. So that's a microstate. Now the question becomes, what happens to our possibility of the number of microstates we can have if we change the volume, or if we were to add another box here and change the volume available to us? How would that affect the possibilities of the number of microstates? Clearly, in this first example, there's only one possible microstate, those four particles in that box. Now, what happens if we double our volume here? Okay, so now you can see I have another box in which to distribute my four particles. And so what are the different number of ways in which I can distribute those particles? So if you stop and think about this for a second, you're probably, the possibilities are probably taking off for you. So I could do something as simply as put all four of those in the other box. That would be a different microstate. Or I could leave one in the box that they're currently occupied and move three over. Well, they're all different atoms, so I would have to do that with leaving the green one behind. Then another microstate would be to leave the red one behind. Okay, so you see what's happening here. Well, what if we left three here and moved one over? Okay, then again, four different particles, so we have a bunch of possibilities there. And then finally, 2 and 2. So you can see here what happens is we get all these possibilities for microstates. Again, here are our microstates, or our possible arrangements, considering the boxes and the four atoms that we had possible here. Okay, so you can see here we have 5 distributions possible. Okay, I started to talk through those a second ago, but we have 5 different possible distributions. And so the one that's most probable would be the one with the most probable distribution would be the one with the highest number of microstates. So we can see here, this distribution of the varying possibilities of 2 and 2 would be our greatest possibility, highest number of microstates. So this is the most probable distribution. Well, what does that mean with regards to entropy? So we can say here that the greater number of possible arrangements that equals the higher the entropy or disorder or randomness. So the larger number of possible arrangements I have, that means the greater the entropy. So again, then another way of saying it here is more microstates equals greater disorder. Okay, and finally we can say here that high entropy is favored because they're more probable. Okay, so different ways of saying the same thing here or similar concepts here is that the arrangement or the distribution with the greatest number of microstates is the most probable because there's the greatest possibility of those, which means then the more microstates there are, the greater disorder, and high entropy is favored because it's more probable. Okay, so that's our connection between entropy and microstates. We could also have done all of this quantitatively as well. So this is a qualitative explanation of how entropy is affected by the different possible arrangements. We could have also used the Boltzmann equation shown here to calculate the entropy in a particular system. This is the Boltzmann equation. And I'm going to develop this a little bit further. So just a couple things here. We see that S is entropy. We have a constant, the Boltzmann constant. Just put a B there. The Boltzmann constant is listed, and then the natural log of W, which is the number of microstates possible here, the number of microstates possible. So I'm going to talk about here in a second how we develop this. But before we get to that, entropy is also a state function, and we know that that means to us that a change in entropy is going to be the difference between the final entropy minus the initial entropy. So with regards to the Boltzmann equation and this part of how we defined entropy with regards to the Boltzmann equation, I can also then say that the change in entropy would be this Boltzmann constant times the natural log of the final over the initial number of microstates possible. Okay, so as I think about the scenario we talked about a second ago with our changing our volume with our four particles, if I were to apply the Boltzmann equation to calculate this, let's first think about how we determine the number of microstates possible. And that equation mathematically, quantitatively, would look like this, okay, where this lowercase n is what I've been referring to as the volume, all right, or the amount of space possible, and the capital N here is the number of particles. Okay, so if we think about that with regards to the scenario that we walked through qualitatively a second ago, we have two possible spaces, okay, 1 and 2, and we have 4 possible particles. So we would get a value here of 16. Okay, and again, that would be with regard to this particular equation. This would be our final possibility, right? Our initial would have just been 1. All right, our space here, our volume here would have been 1. We still have 4 particles, and we would get 1 there as our initial possibilities of microstates. Okay, so now we can plug this into our equation here with the Boltzmann constant as given. Okay, times natural log of 16 over 1, which of course would just be 16, If we solve that out, we would get an answer of 3.83 times 10 to the negative 23rd joules. Okay. If this is our answer, we can see because that value is positive, we would say that we had an increase in entropy, which we clearly saw that as I doubled the amount of space possible, then I got significantly more microstates possible, and so my entropy increased. So we can see both how we did that qualitatively and by considering the microstates, and then quantitatively using the Boltzmann equation. So that's going to be the end of our first video here on section 2. In the next video, we'll talk about how we can predict changes in entropy.